Okay, we're starting today on worksheet 20, notes on probability and probability distributions. The probability of the success or failure of an event occurring would be, the probability of success would be the number of successes divided by all possible outcomes. We're going to be doing combinations for this. Failure, number of possible way of failing, over all possible outcomes. S plus F just represents all possibilities. So let's just look at the coin toss. If you toss 3 coins, these are all the possible outcomes. What's the probability that you get at least 2 heads? So sometimes you need to look at the sample space, and there is a reason to list all this. So if I wanted to know the probability of getting of the 8 possible outcomes, there are 4 that have at least 2 heads. So right here, it says at least 2 heads. So would 3 heads count? Okay. So that's why it was that one, this one, 2 there, and then skip 2 here, and that's it. So 1, 2, 3, 4 occurrences where there's at least 2 heads. So the probability of tossing at least 2 heads was 4 out of 8, or 1/2. What is the probability of picking 4 fiction books and 2 biographies from a bestseller list that consists of 12 fiction books and 6 biographies? The way you do that is the number of successes would be a combination of 4 fiction books out of 12 fiction books. So that's what the 12C4 comes from. Then you wanted to get 6 biographies. There are, or excuse me, 2 biographies out of the 6. So that'd be 6C2. That's where that came from. Success of getting 4 fiction times 2 biographies. These 2 get multiplied, and then you divide by all the possibilities, which there are a total of 18 books, and you're choosing 6 books. So that's where the 18C6 comes from. You calculate this on your calculator, and you get about 40%. I'm going to do both fraction and decimal. Let's do some on our own. All right, so we got a family with 3 dogs and 4 cats. Find the probability of each of the following if they select 2 pets at random to bring to the local pet show. All right, we have the probability of getting 2 cats. So how many cats are there? Thank you. There are 4 cats, so that'd be 4C2. Now, are you taking any of your dogs? But you have dogs. So if you wanted to multiply that 3C0 divided by, there are 7 pets in all, 7 combinations of, how many pets are we taking? Of the 7, we're taking 2 of them. So this is what we would calculate. Now, I would like you to note that 3C0, 3 combinations of 0, you're not taking any. That is 1. Okay? Anytime you have this, you're not taking any of them. It's just a 1. It doesn't make the numerator 0. That's not worth 0. It's worth 1. Now, I don't know necessarily what 4C2 is, so I grab my calculator. Remember that you put in the 4 first, and then you hit math. You arrow over to probability, choice 3, and you put in 2. Okay, that's 6. And then I'm going to do 7C2 while I'm in here. And that's 21. 6 over 21 then is what we get, which could be reduced to 2 over 7, or as a decimal, if I do 6 divided by 21, I'll say it's about 28.6%. You can for that one. You can for that problem. Yes, you could. Yes. Not as far as most of the things we've been answering in a reduced fraction form, so that's why I just showed both of them. Neither one's wrong. Okay. Probability of taking 2 dogs. I just think sometimes when you're thinking of it as a percentage, it means a little bit more in your head than the fraction form, especially when the numbers get really large. So probability of taking 2 dogs, that means you're not going to take any of your cats. Do you really need to write the 4C0? No, because that's actually 1. So it's really going to be 3 combinations of 2 divided by 7C2. We already know 7C2 is 21. So let's find out what 3 combinations of 2 at a time. Oh, I hit the wrong button. Okay then. What'd you guys get? You probably already got it, and I'm Miss Slowpoke. Okay, 3. So 3 over 21, or 1/7, and then again it's a decimal, 1 divided by 7. What's that percentage? Yeah, 14.3. All right, and probably taking 1 cat and 1 dog, we got 4C1 times 3C1. Now, I might want to point out to you that we already know 7C2 is 21. When you have any combination and you're taking just one of them, it's actually that number. Excuse me, it's actually, this is equal to 4 times 3, which is 12. Reducing that would give us 4 over 7. And if we wanted the decimal form, 4 divided by 7 is about 57.1%. Okay. It's up there. Next we have Eduardo with an MP3 player, and he has 10 blues songs and 5 rock songs. They were making fun of this last hour. Find the probability of each of the following if he plays 6 songs at random. Round to the nearest tenth of a percent. 6 blues songs, so he's going to get 10C6. He's not going to take any of his rock songs, so that means 5C0, and you know that's 1. So it can save you some typing. Divided by how many songs in all? He only has 15 songs on his MP3 player. He just started his collection. Okay. Yeah, hopefully he's not done right. I know some of you have just enormous numbers of songs, so I'm just making fun. You should be getting, well, you want to just type it in and get the percentage? It's not a big deal to me, but we do the numerator is 210, the denominator is 5,005, and that reduces to 6 over 143. And if you did divide them out, you would get 4.2%. Okay, 4 blues, then 2 rock, 10C2, 4 I mean, times how many blues songs we have? Oh, we have 5 rock songs. We're going to get 2 of them. And then, of course, that'll be divided by the 15C6. Knowing that that denominator is 5,005, I'm going to just type the numerator. I forgot how many I'm taking. How many of those am I getting? 4 of them? Oh, I can't do that. This thing doesn't like me. I have to get out of there if I want to hit multiply. And then it was 5, and he's going to get 2 of them. All right, so that numerator is 2,100. And then if we wanted, we can just reduce it. I'll just tell you, it reduces to 60 over 143. And a percentage would be 42%. Okay. Now we got 2 blue songs, 10C2 times 5C4 divided by 15C6. You guys are probably faster at typing this in on their calculators than me. Once you try getting that last one. When you hit the math, you can just type it all in and then hit math, enter, as long as you are careful how you type it. 45 over 1001, and it's about 4.5%. Anybody need help with anything about calculating? No? Okay. We're back to some normal old stuff in the moment. So what we're doing here certainly doesn't need combinations. You got one bag of candy with 15 red candies, 10 yellow, and 6 green. What's the probability of getting a red one? Well, it'd be 15 out of 25, 31 of them. Doesn't reduce. 31's prime. B, not picking a yellow. Well, there's 10 yellow, so there's 21 that aren't yellow. 21 out of 31. And getting a green, 6 out of 31. And not picking red, 16 out of 31. Those are pretty easy, right? No? Yeah, I think. Sounds silly. Okay, random variable is a variable whose value is numerical, the numerical outcome of a random event. Okay, it's on the next page. A probability distribution for a particular random variable is a function that maps the sample space to the probabilities of the outcomes in that sample space. Okay, for example, if you were rolling some die, this is the table here is showing the relative frequency. It's called a relative frequency histogram. It's a theoretical happening. Show the distribution of the absolute value of the difference of the numbers rolled. What would difference mean? Yeah, subtract them. So since the highest number is a 6 and the lowest number is a 1, what's the possible outcomes? 6 minus, you're going to do subtract them, and 6 minus 1 is 5. That's how they got the biggest one. And 6 minus 6 would be where they got 0 from if they subtracted them. So you follow where they're getting these from? So this relative frequency table, this histogram, is showing how often what the differences occur when you roll the die. So getting a 0 happens 1 out of 6, 1/6 of the time. Getting 1 is 5/18, 2, 2/9, etc. And this is just a graph of that situation. From looking at the histogram, what is the largest or most common difference? Yeah, the tallest bar, 1. Pardon? Oh, that 4 and 3 could get you a 1. Yeah, 5 and 4 can get you a 1. 6 and 5 can get you a 1. 2 and 1, there's a lot that can get you a 1, right? Where the difference is 1. That's the most common difference. What's the second most common difference? Would be 2. And what's the least common? Getting a 5. Okay? So the greatest probability in the graph is 5/18. That's this one. It goes up to 5/18, and that's illustrated. The most likely outcome is the difference of 1, and the probability is 5/18. Okay, we're going to make a tree diagram of the heads and tails situation, and we're going to flip 4 coins. So, I'm not real great at this, but I liked that one time how we made it where it looked kind of like a butterfly. We're going to have branches over here and branches over there. It really makes it look like a tree. Okay, so what could you flip if you have first choice heads and tails? If you get heads, then you could get for the second flip heads or tails. For the third flip, you could also get heads or tails. And that could happen from both of those last scenarios, heads or tails. How many coins have I flipped now? 3. All right, from there, I can get heads or tails. Bye, good luck. Thank you. That's just fine. And from all of these, you can get heads or tails. My branches are starting to slump. Told you I wasn't great at it. Okay, now I'm going to go to the other side. Heads or tails. And keep going. Bless you. Okay, I'm not going to say it out loud just because I think you can. Oh dear, I think I'm going to crash into my other branches. So before my tree gets messed up, I'm going to make this go down a little further. My branches mashing into each other. Oh, I guess I could have gone there. Oh, Heimer. Oh, Heimer, you're making a mess. All right. Yeah, you know. I haven't said that in a while. Probably good. Okay, there's mine look like a horn, I don't know, sort of like antlers. But here's what we're going to do with this lovely set of data. We're going to find all the possible combinations and we're going to list them because we're going to be making a histogram of the relative frequency of getting different combinations. So the first branch, I'm going to go over here. I'm going to run along my branches to get my combos. 4 H's. We got heads, 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 heads. Then I'm going to go up that, and then I'll turn when I get to the end, and I'll have 3 heads and a tail. Now I'm going to have to turn sooner, 2 heads, then a tail, then a head. And then I'll turn and go the other way, 2 heads, then 2 tails. Okay, now I'm going to the lower branches, heads, tails, heads, heads. Heads, tails, heads, tails. And the last 2, 4, 6, last 2, heads, tails, tails, heads. And the last one, heads, tails, tails, tails. Well, how many tails did I say? I do not know. Okay, that was supposed to be 3. I might have gone too far. All right, that would be all 8 possible combinations at the end on the left side. All right, now we got to list the right side. Start with tails, then 3 heads. Now, I'm not going to say it anymore. I'm just going to write them, and you just make sure you have them all. Okay, your last one should be all tails. Everybody got their sample space? Okay, now we can check the probability of, says complete the table below to show the probability distribution of the number of heads. Okay, so it's about just the heads. What's the probability of having no heads at all? Well, first of all, how many are there here? 2, 4, 6, 8, 2, 4, 6, 8. There were 16. And that comes from rolling 4 coins, 2 possibilities at a time is 2 to the 4th. So there are 16 possible outcomes. We can see that it only occurs once that there are no heads. That's when it's all tails. So that's 1 in 16. How many ways can we have it where in any of these lists that you have exactly just 1 head? So find all the combinations that have 1 head. You're only going to get one of them in, let's see, we got 1 here, 2, oh no, sorry, 1 head. I'm looking at the tails again. Only 1 head. That happens only once in the first left side of the branch. Once. Only 1 head. Twice. 3 times. 4 times. 4 and 16. And that, of course, reduces to 1/4. Well, I'm just going to leave it right now. Exactly 2 heads. Once, twice, 3, 4, 5, 6. I found 6. Is that what you guys got? Which would be 3/8. Okay, keep going. Count how many have 3 heads. It's only 4 out of 16. And 4 heads would be only 1 out of 16. Now, if you note that if you added these all up, 5, 11 plus, you get 16. All of these probabilities add up to 1. Right, let's graph it. 0 was 1/16, so we make a little bar that high. 4/16 is 1/4, so we're going to have to come up here. 6/16 is 3/8, so that'd be at the max. 1/4 and 1/16. So that's the relative frequency histogram. We already knew the probability of 4 heads was 1 in 16. Okay, you're going to be, well, we're almost done with this page. We got a couple more at the bottom. And then we'll be heading to worksheet 21. You are assigned worksheet 24. And 25 is what's going to be the assignment tonight. All right, we got the word arts. The letters A, R, and T are written on 3 different pieces of paper, and the pieces of paper are then put into a bag and mixed up. Logan picks each letter without looking and places them side by side. What's the probability that they spell arts? Well, that's one possibility of A, R, and T. What else could it be starting with A? Okay, ATR. All right, we already exhausted the possibilities of starting with A and having it changed. So let's start with something else. R, RAT, okay, or RTA. That's exhausted the possibilities of starting with R. So now we'll start with T. So you could have TAR or TRA. Okay, so the probability of spelling art is 1 in 6. What if I asked you what's the probability that it spells an English word? Half. Yeah, 3 out of 6, 1/2. Okay, there are 24 students in Miss Mason's 3rd grade class. 11 students are boys. In the morning, the classroom is empty. 1 student arrives, followed by another. What's the probability when the first 2 students arrive that one's a boy and one's a girl? All right, there are 11 students that are boys. There are 24 kids. So how many girls are there? Okay, 13 girls, 11 boys. That's what we know. 24 kids. Okay, probability that the first one arrives as a boy would be 11 C1. Probability the second one's a girl would be 13 C. How many are you taking? 1, which is 11 times 13 actually, divided by how many kids? 24 combinations of 2 kids. All right, the numerator is easy. It's 11 times 13. And the bottom is I don't know. 24C2. 576? 276. So I got 143 over 276. And if you divide that out, it's about 51.8%. Okay, you're assigned 24, and we are going to go over to worksheet. Well, it says it's your worksheet 21, I believe. Probability distribution. The picture is really faded on your packet. Sorry. I want to talk about a few kinds of data. A sample space is a set of all possible outcomes in a distribution. Consider a distribution of values represented by the sum of the values on two die. The sum is when you add. So 1 plus 1 would be the smallest. That's where they get the 2 from. 6 plus 6 would be the biggest, which is 12. That's where that one comes from. And everything in between. What's the most common sum according to the distribution? 7, the tallest one, right? Okay, now, this is countable. All right, this is countable data. Can only be countable is 1, 2, 3, nothing in between. Okay, that is called discrete data. If there's stuff in between, like if you were doing your car mileage miles per gallon that you get in a car, that's this distribution. This is continuous. Anywhere between the max and the min. So anywhere between a range of values. Minimum to maximum number. So it's between there, and it's got decimals involved. So the sum of the values on the dice can be any integer, 2 to 12. That's why it's called the distribution is discrete. All of the possible number values in the space can be counted. Okay. The distribution of miles per gallon is continuous. The sample space includes any possible value between a certain max and a min. The data take on an infinite number of values within this range. Okay, so the value of a random variable is discrete random variable or a continuous random variable. It's discrete if it can be counted, and it's random if it can take on any value in a range. So, what's the difference between discrete and conditional? Might want to write this down. Countable, whole numbers, continuous data has many small amounts within a range. Okay, so it's probably going to have decimals or fractions. Decimals are possible. Okay, so we've got a couple of scenarios coming up on these lovely blurry worksheets. Sorry, my pictures up here are not the sharpest. There's a number of songs found on a random selection of MP3 players. That would be discrete because it's countable. How many songs you have is a finite amount, right? It's going to vary, but it's discrete because it's countable. But the weight of a particular helmet, if it says it ranges from 6 to 8 pounds, that's continuous because it can be values between 6 and 8 decimals. So, what about this example? We're going to decide on this. The exact distances of a sample of discus throws. Continuous? Okay, that is continuous. because you got values are within, the values can be decimals within a range. Now, typically somebody's going to throw it. There's only so far somebody can throw a discus, right? You know, you can't have an infinite bound. It's something, I don't know, whoever's done the longest one, I guess, versus the shortest. Somebody dropped it or something. Anyway, decimals within a range. The ages of counselors at a summer camp. Now, typically nobody says, when you ask somebody how old they are, they usually say, I'm 16, 17, 18, 25, whatever. I don't go, you know, 16.2, you know, you don't do that, do you? All right, they're wanting us to say that this is discrete. Oh, I'm 17 3/4. I'm almost, you know, most people don't do that, right? All right. On the top of the next page. Oh, that's not the top of the, I'm losing where I am here. No, that is. Did I jump too far? No. Okay, example 1. Oh, I was already on that. Oh my gosh, guys, I can't find where I am because my, oh, there it is. My worksheet is so blurred like yours. You see what I'm saying, right? All right, so this is the top of the next page, but that's not it. It's the same thing twice. All right, here we are on 21B. I don't know why I have two pages identical in there. Okay, discrete versus continuous. We want to know what that means. Variables representing height, weight, and capacity will always be continuous because they can take on any positive value. A probability distribution for a particular random variable is a function that maps the sample space to the probabilities of the outcomes within that sample space. Probability distributions can be represented by tables or histograms or equations or graphs. In this lesson, we will focus on discrete probability distribution. A probability distribution has the following properties. It can be determined theoretically or experimentally. You remember the difference? Theoretically is what you expect to happen. And then experimentally is when you actually do an experiment or what did happen. So the probability distribution can be discrete or continuous. The probability of each value of x must be 0 and must be at least 0 and not greater than 1. Okay, so the range of probabilities is between 0 and 1. The sum of the probabilities for all possible values of x must equal 1. That means, and you maybe you don't have seen this notation. I know a lot of you have on those tie-dyed shirts, which means you're in chem. That means the sum. And it's called, yep, sigma. This means the sum of the probabilities of x is 1. That's what that says. Okay, so let's try an example. Remember when I made the sample space of the roll of 2 dice the other day? How many were there in all? Yeah, 36 possible outcomes. That's your sample space. Okay, the theoretical probability is based on what is expected to happen. For example, the distribution of flipping a fair coin, probability of heads is 1/2, probability of tails is 1/2. There's a little star in that box. Theoretical and experimental probability. Theoretical probability based on assumptions and experimental based on experiments. So if x represents the sum of the values of 2 dice, the sum of the values of 2 dice would range from 1 + 1 to 6 + 6. That's why this table has 2 to 12. If you were to add up all these frequencies here, the sum would need to be, well, just if you check it out, that's 3, 6, 10, 15, 21, 26, 30, up 36. Those add up to 36. What should the sum of the probabilities be? Remember, sum is that symbol. Okay, the sum of those should add up to 1, and it does. What, you want to type in all those fractions? Have fun. Go for it. Just kidding. I'm telling you, they add up to 1. It does. It really does. Okay. Well, then you can feel free to type them in. I can change these all to 36 for you. Okay. You're going to believe it? Now, this graph shows the probability distribution for the sum of the values of two die. This is a different representation. The last one was a frequency table. This is a histogram, okay? The bars are separated on the graph because distribution is discrete. That's why the bars are separated. No other values of x are possible, nothing in between. Each unique outcome of x is indicated on the horizontal axis, and the probability of each outcome, p of x, is indicated on the vertical. What's the most common sum of two dies? It's illustrated right there. It is 7. Okay, I'm going to do expected value on Monday. So we're actually stopping right here. They do, don't they? Oh,